In this lesson, we're going to be dealing with powers and roots of complex numbers. This is video number 2 of 2 on this lesson. In the previous lesson, we dealt with writing powers of complex polar numbers such as 2 cis 30 degrees raised to the third power. And we learned that the method was that the coefficient or radius of the polar number was raised to the third power, and we multiplied the angle by the power, so 30 times 3. Which results in 8 cis 90 degrees. One thing you may be asked to do when you are raising the powers is to express the answer in rectangular form. So in this case, we would rewrite 8 cis 90 degrees in what the cis stands for, which is cosine of 90 degrees plus I times the sine of 90 degrees. And we would evaluate the cosine and sine of 90 degrees. Cosine of 90 degrees is 0. The sine of 90 degrees is 1. So we would get 0 plus 8i, or simply 8i, as a result in rectangular form. In the second lesson, we're going to be dealing with roots. So if I wanted to take the square root of 4i, we certainly know how to take the square root of 4, so let's use 4i as an example. Well, first thing we need to recognize is that we want to write 4i in its complete complex form, which is 0 plus 4i. And then change 0 plus 4i into complex polar form. So in order to change it into complex polar form, we need to remind ourselves what that conversion procedure was. We graph the complex form, and we use a complex plane. So if this is the real axis, and this is the imaginary axis, then 0 plus 4i would be 0 in the real direction, 4 in the imaginary direction, and would give us a vector up here from the origin up, and the length of that vector is 4, and the angle at which that vector is from the positive x-axis is 90 degrees. So we could express 0 plus 4i as 4 cis 90 degrees. So now we have our complex number written in polar form, which will allow us to use DeMoivre's theorem. However, we're not going to use an integer as a power. We're going to use the power that 1/2 is, the power that the square root is, excuse me, and that is 1/2. So, we're going to write 4 cis 90 degrees to the 1/2 power. So we have a little bit of an issue to deal with here with roots, and that is we need to remember that when we were dealing with real roots, we had 2 square roots when we were trying to solve for an equation. For instance, if we had x squared equals 4, we realized that x could have been either 2 or -2, resulting in 2 real square roots. Well, it turns out that there are always as many roots as the number of roots you're trying to find. For instance, if I'm finding square roots, that means there's 2 of them. If I was finding cube roots to the 1/3 power, there would be 3. We have only dealt with one of the 3 cube roots to this point in our math career, and that has been the real version of the cube root. However, there are 2 imaginary cube roots that accompany that, for all real numbers. So I need to get 2 answers here when I raise 4 cis 90 to the 1/2 power, and it doesn't seem like DeMoivre's theorem will allow us to do that. So what we need to do is recognize that 90 degrees is not a unique way to describe this vector. It can also be 4 at 450 degrees as well if I go around the circle another time. So I could also call that vector 4 cis 450. If I raise that to the 1/2, we can see what happens. Or I could call that angle, well, if we go around again, that's going to be what? 450 plus 360 is 810. So we'd have 4 cis 810 to the 1/2. And we need to keep playing this game until we make sure that we have all the unique solutions. Now, of course, I've written down 3 here. I'm going to write down a 4th just for emphasis. And that's going to be going around again from 360. So I would have 4 cis. If we add 360, we get 1170, I believe. So now, and I'm going to raise that to the 1/2. So now if I applied DeMoivre's theorem to all these 4, and of course there are infinitely many ways that I could express this, but I think you'll see why I went to 4 just to show you something that's going to happen here. So if we use DeMoivre's theorem here, we would use 4 to the 1/2 power. So erase that. 4 to the 1/2 power. Cis 90 degrees times 1/2. And of course that's 2 cis 45 degrees. Here I would have 4 to the 1/2. 4 to the 1/2 is again 2, and then 450 times 1/2 would be cis 225. And here 4 to the 1/2 again is 2. And 810 divided by 2 is 405. So that would be cis 405 degrees. And if I do this one, I get 2 cis 1170 divided by 2 is, let's see, 1170 divided by 2 is 550, 585 degrees. So let's examine these angles. Well, 45 and 225 we're pretty familiar with. 405 is outside 1 revolution, but this is the same thing as 2 cis 45 because 405 is 45 degrees beyond 360. And this is 2 cis 585 is 2 cis, well, if I subtract 360 from that, I get 225. So you can see that I expressed 4. It turned out that I got the same answer twice by doing that. And if I kept going with these infinitely many other representations of that vector, I would continue to get these two answers, 2 cis 45 and 2 cis 225, infinitely. So it turns out that these 2 cis 45 degrees and 2 cis 225, are the only 2 unique solutions, or I'm sorry, the only 2 unique square roots of 4i. So now if I was asked to write these as rectangular, I would then write 2 times the cosine of 45 degrees plus I times the sine of 45 degrees, which means 2 times cosine of 45 is square root of 2 divided by 2. And the sine is also square root of 2 divided by 2. And if I expand that, I get square root of 2 plus square root of 2i. Oops. Square root of 2 plus square root of 2i. And if I did it for 225, I get 2 times the cosine of 225 plus I times the sine of 225. .225 is in the third quadrant. It has a reference angle of 45, so the cosine and sine are both square root of 2 over 2, but we have to apply the correct sign to them, SIGN. In the third quadrant, cosine is negative and sine is negative, so both of these will be negative square root of 2 over 2. And again, expanding, I get negative square root of 2 minus square root of 2i. So these would be the 2 rectangular representations of those square roots. And if you indeed squared those, you would find that you would get 4i as a result. So the question then becomes, what happens if we want a cube, if we want the cube root? So if I want the cube root of negative 8i, as we spoke before, there's going to be 3 of them. We first have to rewrite this as full rectangular form. So that's 0 minus 8i, which I then have to graph. 0 minus 8i with real axis is in the x direction and the imaginary axis is in the y direction. So down here is -8 in the imaginary direction. So my vector would be right there. It has a length 8 and an angle of 270 degrees. So I would write this, I would write 0 minus 8i as 8 cis 270 degrees. Remembering that when I'm going in the direction of the angle, the radius, the coefficient of the cis, is always a positive number. -8 in front of in a polar means that you're going opposite the angle that you're writing in here. So now I can write this as 8 cis 270 to the 1/3. But again, there's supposed to be 3 answers. So remembering that this is not unique, I would need to write the second form, 8 cis 270 plus 360 is 630. And the third representation, remembering that if we go beyond 3, we're going to just repeat the same ones over and over again, as we saw in the last example. So 8 cis, if I add 360 to that, I get 990 degrees. So now if I do DeMoivre's theorem on this, 8 to the 1/3 is 2. 270 divided by 3 is 90, or 270 times 1/3 is 90. So 2 cis 90 is my first answer. And then 8 to the 1/3 is 2 cis. 630 times 1/3 is 210 degrees. And then finally, 8 to the 1/3 is 2, and 990 degrees times 1/3 is 330 degrees. So one thing you may notice as you do these is that there's a common separation between the angles here. 90 to 210 is 120 degrees, and 210 to 330 is also 120 degrees. And if you look up here, 45 to 225 is 180 degrees. Well, it turns out another way to come up with the other answers, instead of rewriting as the 3 different ways of writing that vector, would be to simply take 360 and multiply by 1/3, and that tells you how much to add between them. So you can get those other 2 answers that way as well. And of course now we could write these in rectangular, since 90, 210, and 330 are special angles. We could expand and come up with exact answers like we did up here for the 2 square roots. Of course, 2 cis 90 should be a recognizable number pretty easily. 2 cis 90 is a magnitude 2 along the positive y-axis, so that would be 0 plus 2i, or simply 2i. These ones, the 2 cis 270 and the 2 cis 330, are going to look like these where they have both components in them. So if I took 2i to the third power, just to verify, if I raise 2i to the third power, we know that just using laws of exponents, that would be 2 cubed times I cubed. 2 cubed is 8. I to the third is negative I. And I indeed get negative 8i. So that just verifies one of them, and of course you could verify the others. So that concludes this lesson on powers and roots. Thank you for listening.